How are you doing, gang? You ready for me to flash the answer to this one? Still working on it? Okay. When you sketch the cell, if you don't, let me just show you the answer, okay? Grace, don't look. Here's why you have to balance it. Because the left side is no big deal. It's just the oxidation of iron, and there's no surprise there. But over here, you look at what's inside of the container, and if you didn't balance it, you're going to ask, what's that hydrogen doing there? But if you did balance it, you know exactly why that hydrogen is there. Yes? Because hydrogen is part of the half reaction of the permanganate reduction. You see what I mean, Natalia? Does that make sense? So you had to have balanced it to see what else was in there. So let's see. I forgot what I asked you for. Number one, sketch, and number two, anode and cathode, of course. As I said before, I always go anode on the left and cathode on the right. Oh. Okay. Why are we using platinum instead of manganese? Manganese is, the metal manganese is not a product, nor is it a reactant here. So you shouldn't put it in there as a bar, because the manganese may actually react and become part of the reaction, which would not reflect this reaction. Okay? So I was going to address that too. I'm glad that you asked that. Yeah, when you have one ion changing to another, use platinum. Use an inert conductor. Because you know, because it's inert, it won't get involved in the reaction. Because you may wind up having permanganate reduce all the way to Mn if you have Mn as an electron. Now the line notation. Let's take a look at that line notation, because this one is different from the last two that we did. Remember on the line notation, the double bar means, or the double line, means that separates the anode from the cathode. So we have anode on the left of the double line, cathode on the right. So the anode, we have iron oxidizing to Fe+2. Remember, the single lines represent a change in physical state. You've got a solid on one side of the single line, and then an aqueous thing. So you've got a different physical state that it goes to. Now over here, our reactants and products are all aqueous. So you don't put a line between them, even though you would think that you would separate the products from the reactants. Because they're all the same physical state, we don't. We do need to acknowledge what the reactants and what the products are. So the reactants in this case are the permanganate ion in the cathode and hydrogen ion. The hydrogen is on the left. It's a reactant. And then the product of this thing is the Mn+2, the manganese 2 ion. Platinum is the electrode, so that goes last. Now, all three of these are ions, and then so they're aqueous, and then the platinum is a solid, so we need to separate those with a single line. So when people ask, does it matter what order they go in? Yes, it matters. The reactants have to go first, and then the products, even though we're just doing commas in between them. We have two reactants in this one. We have permanganate ion and hydrogen. Between those two reactants, it doesn't matter what you put first. But make sure that the reactants come first and then the products. Again. Line notation is strange. Electrochemistry is the only place we ever see it and use it. Can I answer any other questions about this one? I have one more for you. This last one won't take as long. That one took a long time. Okay, we all good with this slide? Would you do this one? That one looks like it's going to take a long time, but you're given both half reactions. And I want to remind you, on the quiz, there will be a question like one of these. One of the 5 is for sure going to be sketch the cell, show the direction of electron flow, give the overall balanced equation, that kind of thing. So be ready, and that's why I'm giving you so many examples. This is a big part of the chapter.
Well, it's almost like you're in college. You know what it is. I wrote down the question. You have to flip the oxidization. So,
No, you have to balance it. She did that. She just added
pretty sure MnO4 is a reduction.
No, she put like 10
Yeah, so you flip, you you flip the I one. I know, but you flip the one that. Yeah. I'm pretty sure you flip the. No, we just said MnO4 is negative.
Yeah, the iron goes on. You don't flip this. This already counts. It's already flipped. That's already flipped. Look right there. So you have, there's iron.
It's got to be positive. Make sure you turn the red one around so to make it positive.
Yeah, let's get on one.
So you flip the one to get positive, or you flip a specific reaction? So you flip it in order to get positive. You don't flip. So apparently you don't. It doesn't matter if the oxidation reduction. You just want the voltage to be positive. So in order for
Huh.
I just figured that out.
8 minus 2 is 6.
I thought, but in this case, I'm flipping the. No, that's only when we find the top.
I don't like you either. You said I don't like you. No, you don't.
Okay, so this is the
So
top
what's
one.
16 minus 10?
Why?
6.
When?
Yeah, I know it's gonna be 6.
Oh, okay, good job. I know it.
Plus 5.
Ready? to admit that the cell potential for this thing is so anticlimactic, it just is deflating. Anybody pick up on that? After you've done all that work, you look at the cell potential and think, oh man. All right, here it is. We need platinum in both sides because in both cases there's ions making ions, so neither side has a metal in the half reaction. They both needed hydrogen, but those half reactions were given to you. Don't forget them. This is what I'm talking about, the cell potential. After all that, we get a cell potential of 0.09 volts. Why even bother? This thing is it's almost neutral. We're certainly not going to use this reaction to power our new Tesla, are we? So yeah, we had a sketch. We had to show the direction of electron flow from anode to cathode. So no big surprise. Once you've done a few of these, you know, you have to get the feel of turning the reaction around, balancing it by getting the electrons the same. But that comes pretty quickly. Add the two cell potentials together, well, oxidation and reduction potential together. Can I answer any questions about this one? It has to be a spontaneous reaction with positive voltage. If you have negative voltage, it just means that the electrons are going to go the other way. They'll always go in the spontaneous direction. Anything else about this one? So yeah, when you're deciding, you're given both half reactions. These are both written as reductions. You got the electrons on the left and on the left. So they're both reductions. One of them has to be turned around. You're just going to take the lower one to turn around so that when you add them together, you get a positive voltage. And then you, of course, have to balance it by getting the number of electrons the same. Okay, so you're well equipped to try some of the problems now in the homework. And just one other thing for today is I wanted to talk about the battery lab. That happens a week from today, next Tuesday. By next Tuesday, I want you to bring in some things from home or from a store that you can use to create a voltage. Now, I will have any supplies that you need in terms of lab equipment. Any beakers that you want to use, salt bridges, porous cups, wires, the voltmeters, anything that you can get from class you can plan on. I'll talk about this later, not today, but you can use a 1-cell or a 2-cell setup. When you have a galvanic cell, you've got two parts to it. There's the anode and the cathode. You can actually connect two galvanic cells together and double your voltage. And the object is going to be to try to maximize your voltage. You want as much voltage as possible, because if you're in the top 3, there's extra credit available to you. The highest voltage in the class, assuming your written part of the lab is right, you'd get a 15 out of 10. So it's worth 5 extra credit points. Yeah, and I think it's the only extra credit that I've offered all year, if I remember. That's right, being the special